Welcome to Raw History. This is where we cut through romanticization and speculation to show you the unfiltered reality of human history. The illusion of stone timber's true dominance. Walk through the ruins of any medieval fortress today and, well, your eyes immediately gravitate toward the imposing stone walls, the crumbling towers, and the weathered battlements. This visual dominance has created a persistent misconception that medieval military architecture was exclusively a story of quarried rock and mortar. But the reality preserved in construction accounts, archaeological surveys, and surviving structures tells a radically different tale. Timber formed the structural backbone of most medieval fortifications, with stone often serving as little more than protective cladding over massive wooden frameworks. The Great Tower at Bodiam Castle in Essex, completed around 1140, stands as compelling evidence. While its exterior presents solid stone construction, examination of the interior reveals floor joists, roof trusses, and wall reinforcements entirely dependent on sophisticated timber engineering that predates the stone facing by several construction seasons. Economic records from the reign of Edward I of England provide hard numbers that, honestly, illuminate this timber-first reality. Between 1277 and 1304, Edward's Welsh castle-building campaign consumed extraordinary resources, yet timber expenditures consistently matched or even exceeded stone costs in the surviving pipe rolls and building accounts. The construction of Beaumaris Castle, beginning in 1295, required 2,630 tons of timber delivered in the first 18 months alone, compared to roughly 3,200 tons of stone during the same period. Master carpenter James of St. George, who directed much of this work, commanded wages equal to the master mason, a detail that would seem bizarre if timber work was merely supplementary. The logistical challenge of moving massive oak beams from royal forests across Wales required dedicated road construction, river barge systems, and ox teams numbering in the hundreds, investments that make no sense unless timber formed essential structural components. The ingenious joint more than just wood. The medieval carpenter's true genius resided not in the wood itself, but in the joints that transformed individual timbers into monolithic structures capable of withstanding both gravity and violence. The mortise and tenon joint, refined to extraordinary precision by the 13th century, created connections stronger than the wood surrounding them. Archaeological analysis of the timber frame, excavated from the collapsed roof of York Minster's south transept, originally constructed between 1220 and 1241, revealed mortise depths averaging 7 inches, with tolerances of less than 1/16th of an inch. These weren't approximate fits carved with rough tools, but precision engineering executed with specialized augers, chisels, and measuring devices that allowed timbers weighing several tons to slide together with minimal force, yet remain immovable under stress. The dovetail joint represented an even more sophisticated solution to specific structural challenges, particularly where lateral forces threatened to pull timbers apart. Master carpenters working on defensive structures employed compound dovetails, where multiple angled cuts created mechanical locks that grew tighter under tension. The gatehouse at Stokesay Castle in Shropshire, built around 1291, preserves original dovetail connections in its drawbridge mechanism housing. Engineering analysis conducted during 1980s restoration work demonstrated that these joints could withstand pulling forces exceeding 12 tons before failure. Far beyond what siege equipment of the era could generate, the tapered geometry meant that the harder an enemy pulled or battered the structure, the more firmly the joint locked together, a principle of mechanical advantage that wouldn't appear in formal engineering texts for another 4 centuries. Scarf joints solved the problem of creating continuous beams longer than any single tree could provide, essential for spanning wide halls or supporting extended wall sections. The stopped, splayed and tabled scarf joint, documented in construction manuals from the early 14th century, distributed stress across multiple contact surfaces while using wooden pegs driven through precisely aligned holes to prevent slippage. The collar-braced roof structure of Westminster Hall, rebuilt between 1393 and 1401 with a clear span of 68 feet, relies on scarf joints to create continuous tie beams from timbers that individually measured only 35 to 40 feet. These connections have borne the weight of the hammerbeam roof for more than 6 centuries without detectable movement, a durability record that many modern steel connections struggle to match. Beyond the walls, integrated timber systems really pushed medieval engineering to its limits. The defensive functions of medieval fortresses demanded timber engineering at its most inventive. Drawbridges required not just strength but precise balance and, well, smooth operation under combat conditions. The surviving mechanism at Bodiam Castle in East Sussex, constructed in 1385, employed a counterweight system housed entirely in timber frames. Oak beams 40 feet long and 18 inches square formed the pivoting arms, connected through massive iron-bound pivot joints to vertical timbers embedded 15 feet into the gatehouse foundation. Contemporary accounts describe these bridges operating smoothly enough that 2 men could raise a span weighing over 3 tons, yet the structure could withstand the impact of a loaded siege tower without failing. The secret lay in the distribution of forces through multiple timber members, each carefully proportioned to flex slightly under extreme loads rather than fracture catastrophically. Hoardings, those temporary wooden galleries projecting from castle walls during sieges, really show us medieval carpenters working under, well, the ultimate pressure test. These structures had to support armed defenders, withstand missile impacts, and, remain stable while cantilevered 12 feet beyond the wall face. The construction manual attributed to Villars de Honnecourt, dating to roughly 1225 to 1235, actually illustrates the timber framework for these galleries with quite remarkable detail. Diagonal bracing members transferred vertical loads from the platform back into the wall through angled connections, while horizontal ties prevented the structure from pulling away. Archaeological evidence from the siege of Kenilworth Castle in 1266 includes charred timber fragments showing these exact connection patterns, confirming that theoretical designs translated directly into battlefield construction. The relationship between timber frames and stone curtain walls, well, it deserves particular attention as it really upends our mental image of how these structures functioned. Rather than stone walls supporting themselves purely through mass and compression, many medieval fortifications actually employed timber frames as the primary load-bearing skeleton, with stone serving as protective infill and facing. Excavations at the Bailey Wall of Hendoman in Wales exposed this construction method in cross-section. Oak posts standing 20 feet tall were set 8 feet into the ground at 12-foot intervals, connected by horizontal beams at ground level, mid-height and wall top. Stone and rubble filled the spaces between these timber members, creating the appearance of a solid stone wall, while the timber frame carried the actual structural loads. This technique allowed walls to rise quickly and economically, while still achieving the visual intimidation factor of stone construction. Durability by design. Why did timber endure? The survival of medieval timber structures for, 7, 8 or even 9 centuries really contradicts modern assumptions about wood's durability, yet the evidence stands throughout Europe. The parish church of Greenstead in Essex, for example, contains nave walls built from vertically split oak logs dated through dendrochronology to between 1053 and 1063, making them over 960 years old and still structurally sound. This longevity resulted from deliberate design choices rooted in empirical understanding of material behavior. Medieval builders recognized that timber decay occurred primarily where moisture accumulated, so they engineered protection into every detail. Stone plinths, elevated wooden sill beams above ground moisture, generous roof overhangs kept rain away from wall timbers, ventilation gaps between timber frames and stone facing allowed air circulation that prevented condensation. Chemical protection played an equally vital role. Lime wash, which is basically a mixture of slaked lime and water, was applied liberally to exposed timbers in cycles documented in estate management records. The accounts from Dover Castle show lime wash application to timberwork occurring every 3 to 4 years throughout the 14th century, creating an alkaline surface that's hostile to wood-boring insects and fungal growth. Tarring, particularly for timbers in contact with ground or water, appears repeatedly in construction specifications. The 1256 building contract for the timber revetments protecting the Thames side approaches to the Tower of London explicitly requires all below-water timbers to receive 3 coats of pine tar, heated until it penetrated at least half an inch into the wood surface. Modern analysis of preserved medieval timbers shows this tar treatment creating a hydrophobic barrier that remarkably remained effective for decades. Perhaps most impressive was the temporal vision embedded in these structures. Master carpenters selected timber species and sizes not for immediate needs but for projected lifespans measuring in centuries. The practice of using green oak, timber felled and worked, while still containing natural moisture, allowed joints to tighten as the wood dried and shrank over the first 50 years of a building's life. Specifications from the 1340s construction at Windsor Castle call for oak trees of at least 80 years' growth for primary structural members, with the understanding that slow-grown dense wood from mature trees offered superior strength and decay resistance. This willingness to invest in materials whose full properties wouldn't manifest for generations reflects a cultural relationship with time that modern construction has largely abandoned. Modern echoes. The resurgence of timber framing. Contemporary architects and engineers increasingly recognize that medieval timber technology offers solutions to current challenges around sustainability, carbon sequestration, and seismic resilience. The mass timber movement, employing techniques like cross-laminated timber and glue-laminated beams, echoes the medieval insight that properly connected wood can outperform steel and concrete in specific applications. The joint designs pioneered by medieval carpenters reappear in modern timber engineering, often without acknowledgement of their historical precedents. Japanese temple carpenters, whose tradition paralleled European medieval practice, have successfully advocated for traditional joinery in earthquake-prone regions, demonstrating that flexible timber connections outperform rigid steel in absorbing seismic shocks. The environmental argument for timber construction grows more compelling as climate concerns intensify. A cubic metre of structural oak sequesters approximately 1 ton of carbon dioxide, while requiring a fraction of the embodied energy needed to produce equivalent steel or concrete. Medieval builders achieved this environmental benefit accidentally through economic necessity, but their methods provide a proven template for modern sustainable construction. The challenge lies in recovering the craft knowledge encoded in surviving structures and historical documents, knowledge that industrialized construction largely discarded during the 19th and 20th centuries. Standing before a medieval fortress, look past the stone to imagine the hidden timber skeleton that made such structures possible. The carpenters who shaped those joints with hand tools and geometric principles deserved recognition equal to the masons who dressed the visible stone, yet history has largely forgotten their names while preserving their work. Their legacy endures not just in scattered surviving buildings, but in techniques that modern engineering is only now rediscovering and validating through computer modeling and materials science. Subscribe to Raw History, and share this investigation with anyone interested in the hidden engineering that shaped our built environment. The strongest fortresses were never just stone and mortar. They were testaments to the unsung brilliance of medieval timber craftsmanship that still has much to teach us today.